Right now, as you're watching this, there are roughly 400 billion stars in our galaxy alone, and our best math tells us that a significant fraction of those stars have planets. And a fraction of those planets sit in what we call the Goldilocks zone, not too hot, not too cold, where liquid water can exist. We're talking about billions of potentially habitable worlds in just our galaxy. And we've been sending radio signals into space since the 1900s. Our television broadcasts, our radar pulses, our military transmissions, they've been expanding outward at the speed of light for over 100 years now, a bubble of human noise 200 light years wide, washing over thousands of star systems. So where is everybody? Why hasn't anything written back? Now, you've probably heard the dramatic answers. Maybe they're hiding. Maybe we're in a simulation. Maybe they already came and left. But here's what I want to do today. I want to give you the physicist answer. The one that doesn't require conspiracy, doesn't require mystery, doesn't require aliens to be sinister or shy. I want to show you that the universe itself, the laws of physics as we understand them, may be the greatest filter, the greatest wall, the greatest moat ever constructed. Not by any civilization, just by nature. And when you really understand why, you'll never look at the night sky the same way again. Let's start at the beginning. When I was young, I remember reading that the nearest star to our sun is called Proxima Centauri, and it's 4.24 light years away. Now, light years is one of those phrases that gets thrown around so casually that we stop actually hearing it. So let me fix that. Light travels at about 300,000 kilometers per second. That's fast enough to circle the entire Earth 7 times in 1 second. 1 second. In 1 year, light travels roughly 9.46 trillion kilometers. Proxima Centauri is 4.24 of those years away. So if you built the fastest spacecraft humanity has ever launched, the Voyager 1 probe, currently the most distant human-made object, it travels at about 17 kilometers per second. At that speed, to reach Proxima Centauri, 73,000 years. 73,000 years. The pyramids of Giza are 4,500 years old. Agriculture, the thing that made civilization possible, is maybe 12,000 years old. We're talking about a journey 6 times longer than all of recorded human history, and Proxima Centauri is our neighbor, the closest thing to us in an ocean of nothing. Now here's the thing. A sufficiently advanced civilization could build a much faster ship. Let's be generous. Let's say they crack some extraordinary engineering and hit 10% the speed of light. That's unimaginably fast. It would take more energy than the entire current output of human civilization to accelerate even a small craft to that speed. But let's just say they do it. At 10% the speed of light, Proxima Centauri is 42 years away. Better, still a human lifetime, but conceivable. But here's the brutal math. The Milky Way galaxy is 100,000 light years across. Even at 10% the speed of light, crossing it takes 1,000,000 years. And that's just our galaxy. The nearest large galaxy, Andromeda, is 2.5 million light years away. At 10% the speed of light, that's 25 million years of travel. The universe is 93 billion light years across an observable diameter. The scale isn't just large. It's almost conceptually violent. The distances are so enormous that even light, the fastest thing that can exist, takes geological epochs to cross them. But okay. Maybe an alien civilization is so advanced they can go faster. Maybe they've figured out warp drives, wormholes, something we haven't. Fair, so let's talk about that. Let's talk about what physics actually says about going in 1905. A 26-year-old patent clerk named Albert Einstein published a paper that quietly and without much immediate fanfare broke our understanding of the universe. He didn't discover the speed of light. We knew light was fast. What he showed was something weirder. The speed of light isn't just a speed. It's not like the speed of sound, a property of a particular medium that you can beat with a faster vehicle. No, the speed of light is a fundamental constant of the universe itself. It's baked into the structure of spacetime. And here's the consequence that ruins everyone's dreams of galactic travel. Nothing with mass can reach the speed of light. Ever. Not it's difficult. Not we'd need a bigger rocket. The mathematics equations that have been verified by a century of experiments to extraordinary precision say that as any object with mass accelerates toward the speed of light, 2 things happen simultaneously. First, the object's effective mass increases. It takes more and more energy to accelerate it further. As you approach the speed of light, the energy required approaches infinity. You cannot reach light speed because doing so would require infinite energy. And the universe doesn't have infinite energy to spare for your road trip. Second, And this one is delightfully strange. Time slows down for the traveler. This isn't a metaphor. It's not a psychological sensation. It is a real, measurable, demonstrated effect called time dilation. We've measured it with atomic clocks on airplanes. We've measured it in particle accelerators. GPS satellites have to account for it in their software, or your navigation would drift by kilometers per day. Here's what that means for space travel. If you could somehow travel at 99% the speed of light, an engineering feat so vast it staggers the imagination, time for you slows to about 1/7 the rate of people back home. You leave Earth. You travel to a star 70 light years away. Your clocks, your heartbeat, your aging, all proceed normally for you. The journey feels like 10 years to you, but when you arrive, 70 years have passed on Earth. Everyone you knew is dead or very old, and you're still only 70 light years from home, in a galaxy 100,000 light years wide. Now, I know what you're thinking. You're thinking, what about wormholes? What about warp drives? What about bending space? This is where physics gets genuinely, gloriously complicated, because the equations of general relativity, Einstein's other revolution, the one about gravity, technically do allow for solutions that look like shortcuts through space. Wormholes are real solutions to Einstein's equations. They're not forbidden by the math. The problem is the fine print. A stable, traversable wormhole almost certainly requires something called exotic matter, matter with negative energy density. As far as we know, this either doesn't exist in usable quantities, or exists only at microscopic quantum scales we can't harness. The Alcubierre warp drive, a theoretical spacetime bubble that compresses space in front and expands it behind, would require an amount of exotic matter with negative mass equivalent to the mass of Jupiter. Negative mass, of which we have found none. These aren't engineering problems. They're not build a bigger collider problems. They are potentially fundamental problems with the fabric of reality. Physics so far is very consistent on this point. It has a speed limit, and it is ruthlessly enforced. Let's set aside faster than light travel for a moment and just ask, what would it actually take to cross interstellar distances at, say, a reasonable fraction of the speed of light? Let's do the math together. This is the fun part. Say you want to send a spacecraft, a modest one, 100 tons to a nearby star at 10% the speed of light. The kinetic energy of that ship would be roughly 4.5 times 10 squared joules. To put that in perspective, the entire world's current energy production in a year is about 5.8 times 10 squared joules. So to send one modest ship to the nearest star at a tenth the speed of light, you need to spend nearly the entire annual energy output of human civilization. And that's just to get it moving. You haven't slowed it down at the other end. Deceleration costs roughly the same. And then there's life support, shielding against interstellar dust at 10% light speed. Even a grain of sand hits like a small bomb. Communications. Now a truly advanced civilization, a Kardashev Type 2 of the 3 civilization, might harvest the energy of their entire star or galaxy. So maybe in principle they have enough energy, but here's the second brutal constraint. Interstellar medium. Space is not empty between the stars. There's a thin soup of hydrogen atoms, dust, cosmic rays. At 10% the speed of light, these particles hit your spacecraft with tremendous relative energy. You need shielding. Heavy shielding adds mass. More mass requires more energy. The engineering compounds in vicious feedback loops. Some proposals, like the Breakthrough Starshot project, propose sending tiny gram-scale laser sail probes to Proxima Centauri at 20% the speed of light. Tiny probes, no crew, no deceleration. Just fly by. Even that requires a laser array of 100 gigawatts, sustained for minutes. That's roughly the entire electrical generating capacity of the United States focused into a single beam. To send people, to stop them when they arrive, to send them home. The numbers become almost theologically large. Now, I'm not saying it's impossible forever. I'm saying that for any civilization anywhere close to our technological level, it is effectively impossible. And given the age of the universe, most civilizations that exist, if they exist, are probably not vastly more advanced than us. The ones that are would have to have survived for millions of extra years, beating every extinction filter thrown at them. In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos. They'd been joking about a recent cartoon about aliens. And somewhere in the conversation, Fermi just asked quietly, simply, "But where is everybody?" That question became one of the most famous unsolved problems in science. The Fermi Paradox, here's the argument in its simplest form. The universe is 13.8 billion years old. Earth is only 4.5 billion years old. That means there were billions of years before Earth even formed, during which life could have evolved, gotten smart, and started spreading. Even if interstellar travel is slow, even if you can only go 1% the speed of light, a civilization that started colonizing space just a few million years ago could have, in principle, colonized the entire galaxy by now, not every star. But enough that we'd have noticed, but we haven't noticed anything. No signals, no megastructures, no von Neumann probes replicating through the galaxy. No footprints in the cosmic dirt. The universe is loud with electromagnetic noise, and yet when we point our telescopes at it, deliberately listening silence. Why? There are several categories of answer. Let me give you the physics-honest ones. Answer 1. The distances are simply too great. This is the answer this whole video has been building toward. Even a civilization a million years more advanced than us may simply find that interstellar travel is not worth it. The energy cost, the time cost, the risk, perhaps every advanced civilization eventually concludes, stay home, build inward, not outward. The galaxy isn't colonized because physics makes colonization genuinely prohibitively hard. Answer 2. Civilizations don't last. This is called the Great Filter Hypothesis, and it comes in two terrifying flavors. Flavor A, the filter is behind us. The incredibly unlikely event, the origin of life, or the development of complex cells, or the evolution of intelligence, is so improbable that we might simply be the first civilization in our galaxy to reach this point. We beat the cosmic lottery, we're alone, or nearly so. The universe is full of dead planets and missed chances. Flavor B, the filter is ahead of us. Every civilization that reaches our level of technology eventually destroys itself. Nuclear weapons, engineered pandemics, AI misalignment, climate collapse, something we haven't imagined yet. The reason we see no advanced civilizations isn't because they never arose. It's because they all died. And we're next. I find this the most genuinely unsettling idea in science, because the discovery of simple life on Mars or Europa, which would normally be cause for celebration, would actually be terrible news under the Great Filter Hypothesis. It would mean life is common, which means the filter isn't the origin of life, which means the filter is probably ahead of us. The more life we find elsewhere, the scarier our future becomes. Answer 3, they're here and we can't detect them. Maybe advanced civilizations communicate with methods we haven't discovered yet. Neutrino communication, quantum entanglement messaging, gravitational waves. We've only been listening with radio telescopes for about 70 years. We were looking at the ocean floor for barely a moment before concluding there were no fish. Now I want to tell you something that Feynman used to say in a different context, but which I think applies perfectly here. He said, I would rather have questions that can't be answered than answers that can't be questioned. The Fermi Paradox, the light speed limit, the energy wall, these aren't failures of imagination. They're invitations. They're the universe handing us a puzzle and saying, I dare you. Here's what we know for certain. The speed of light is real, verified, tested. It is not going away. The energy required for interstellar travel is real, enormous, not infinitely large, but genuinely staggering for any civilization that hasn't mastered the energy output of stars. The distances are real, unimaginably vast. The nearest star is 73,000 years away at our current best speed. And yet, and this is important, none of this proves we are alone. It only proves that visiting is hard. Information can travel at the speed of light. Signals can cross the galaxy. Mathematics is the same everywhere. The laws of physics that I've been talking about tonight are the same laws that govern every atom in every star in every galaxy. Any civilization smart enough to survive long enough will discover the same equations we have. We share a language with every intelligent being in the universe. The language of physics, maybe that's the answer to Fermi's question. Maybe the universe isn't silent. Maybe it's just that conversation is what survives the distance. Not bodies, not ships, not physical presence. Maybe the universe is full of minds talking across the void, and we're just learning to listen. We've only been in this club for about 100 years. We're the newcomers. We're the civilization that just figured out radio. We're still building our first real telescopes pointed outward with serious intent. Give us time, and maybe, just maybe, the reason no alien has landed on the White House lawn isn't because they don't exist. It's because physics is the same for them too. They face the same wall we face. They look out at the same impossible distances and do the same math and reach the same staggering conclusions. We are separated not by indifference, not by fear, not by some galactic conspiracy. We are separated by physics, and somehow I find that more beautiful than any other answer. This is actually a reasonable position, but it doesn't solve the physical problem of getting here in person. You can send a signal at the speed of light. You cannot send yourself. If this made your brain hurt a little, good. That means it's working. The one thing I'd ask you to do is this. Go outside tonight if you can. Look up. Find a patch of dark sky and just actually try to feel the distance. Not to think about it abstractly, but to feel it. That faint smudge above you isn't a decoration. It's a galaxy, billions of suns, inconceivable distance. And then come back and tell me in the comments, does the distance make you feel small? Or does it make you feel like we're the most astonishing accident in the known universe? I genuinely want to know. If you want to go deeper on any of these topics, the Fermi Paradox, time dilation, wormhole physics, or the Great Filter, I've linked the best papers and explainers I know in the description. No fluff. Real sources. Subscribe if you want more videos that treat you like you're smart enough to handle the real physics, because you are.